What's happening, YouTubers? It's Alan here. 5-3, the fundamental theorem of calculus, FTC for short. We're obviously going to be going over something huge in this section. It's fundamental, this theorem is, to calculus. I mean, what more can I say? A lot of important stuff. This is finally going to allow us to do all the things that we've tried to just introduce in the first two sections, and that is find the area under a curve from some A to B interval. We're going to start with 531 called the mean value theorem. And if you remember what we just ended with in the previous 5.2 was the average of a function. And the way that we found it was by taking the antiderivative from A to B, but in order to have the average, then we needed to have divided by the B minus A, the difference or distance from A to B. Well, what this is saying, this mean value theorem, is again implementing that there's going to be some average value. And if our function is continuous on that closed interval, then what this theorem has been proven is that there will be at least one value in that interval that makes this true. Hence the name, the mean value theorem. Now, if you don't like the form of this, you could actually take this nasty fraction, and the way that we undo dividing is multiplying. And that would allow us to actually multiply both sides of this equation by b minus a and have just the integral by itself. And that would look like b minus a times that value. Well, obviously, if we're looking for c, we want all of this by itself. Either or, as far as the way that we can write it, normally we can just do this and then multiply by that to then find that, which remember, can be more than one mean value. Now, let's get to the namesake, which is the fundamental theorem of calculus. Unfortunately, there are two parts to it. So let's start with the first. Now, obviously, part one is the first because it's important. It's, I don't want to say more important, but without it, everything else doesn't quite hold. So we're going to go over this one first, even though we're actually going to use part two more often. So what is the fundamental theorem of calculus? Part one. Look how they start again. Continuous on a closed interval. If that is true, then we know that there aren't any issues like holes and asymptotes and all those things that make limits and therefore derivatives or antiderivatives or integrals have problems. And what this says is if your antiderivative of some function from a to some other variable, some unknown, if you were to integrate this, then we would just call it capital F so we don't have to write all of this. But if we did that and then found the derivative of this thing, which is our antiderivative, then what do you think would be the result? Think about that. And if you want to pause to give yourself more time to think about it, I encourage you to. But what is the fundamental theorem of calculus saying? If we have an antiderivative of something in terms of t from some number to some unknown value we're calling x, then we would obviously be able to then take the derivative of that function we're calling capital F, and when we do, it will just merely undo what we just did, which was the antiderivative of it, by taking the derivative. But you don't actually get what you might think. It's not just this, because what we would have done is find the area from a to x, which means now this is going to be in terms of x. A is just a number. So when we go and take the derivative of our antiderivative, those are inverse operations, like adding and subtracting, multiplying and dividing, squaring, square rooting, exponential functions, and logarithmic. All of math has to have its kryptonite, a way to undo it. We call it the inverse. And that's exactly what this is stating, and this is what it yields. Again, noticing that it changed from t's to x. Now, of course, this can be made a little bit more arduous by not just putting x, which represents some unknown value. You can actually put another function up there. And if we were to take the derivative of that, remember, we would obviously take and get our original back, but we would also have a chain rule, which would also yield our dx. We didn't write it on this one because it was with respect to x, and therefore it's just a 1. So what would that look like with some other function rather than just x? We'll see a little bit later, but we'll give it another name just to kind of clean things up, keeping in mind that we may have to take, when doing the derivative of more than just an x, since that's what we're taking the derivative with respect to, if it's anything other than that, we would have to do the derivative of it as well. So that's the fundamental theorem. What is it basically saying? Is that the derivative and the antiderivative are inverses. In other words, one undoes the other. But recall I said earlier that part 2 is the one that we'll actually utilize the most. So let's get to that one. You couldn't tell it was important. I tried to put 3 stars around it to let you know, hey, this is the one that we are going to see and use the most. And of course, it has to be continuous over the closed interval. And what it says is that if we take the antiderivative or integrate our function from a to b, what we can do is take that antiderivative, which we're calling capital F of the lowercase original function that we are given here, taking the antiderivative of, and all you have to do is once you've found that antiderivative, f of x, then you will take the upper limit and evaluate it and find the difference of it and the lower limit. And if you remember what we've been talking about the previous 2 sections of this chapter, is what this finds for us, is the area under our curve, which we said with Riemann, we could take the length and the width of a bunch of rectangles from this a to b interval, and that would give us, unfortunately, the approximate with the left or right or even a midpoint of however many rectangles. But now notice this has the equal sign, not the squiggly approximate, which is why it is fundamental to calculus. This finds the exact area under this curve from a to b, and it's just by doing this. Whatever the antiderivative of that little f is, you plug in the b, the upper limit, you plug in the a, the lower limit, and you subtract. Yes, let that sink in. That is it. Way better than what we did with Riemann and cutting it into a bunch of little rectangles. And then eventually saying, what would be the best number of rectangles? Well, as many as you can possibly draw and find the area of. And that was the limit process that we introduced and then took out the Greek uppercase letter S. And with that limit, we stretched it to our uppercase S by adding in the limit for n going to infinity. And all we have to do is that. Beautiful. This is amazing. That's why it is called the fundamental theorem of calculus. It will find the exact area under that curve. And that is all there is to it. Pretty rad. That's all we have to do. But of course, that means then all we have to make sure that we can do is integrate and evaluate. So I hope you do appreciate the brilliance of the simplicity that this allows us to be able to find the things that we're now challenged with finding without having to do hardly any work at all. And the nice thing is, that's it for this so very important section. But I would like to do at least one example of this fundamental theorem part 2 with you, the one that we're going to utilize the most, just so that you can appreciate this in all that we have to figure out now. So let's do an example together. Now I'm just going to do the first one with you just to kind of keep it simple, make sure that you understand the process. And again, without me saying this, you should know that that's what you get to use in order to evaluate these integrals. You don't have to go and draw y equals x squared from 2 to 5 and try to figure and cut and left or right or No. All you got to do is what it says, and that's integrate. And what do we know? We can integrate x to a power by just adding 1 to the power and dividing by that power. Now, if you do that, you get x cubed over 3. And the way that we're going to write this is we're going to now take this because we've done the integrating. We took the antiderivative of x squared, my length and width, my area under the curve, but I need to do it from 2 to 5 still. Now, if you're wondering where the plus c went, check it out. If I did the f of b minus f of a, and you kept the plus c here and you kept the plus c here, well, when you subtract, the c's would then just cancel out, which is why we don't need to see that c when it is defined over an interval. So if you're wondering where that went, that's where it went. And all we are tasked with doing is plugging in our upper limit and subtracting our lower limit by evaluating it into the antiderivative of our original. So plugging in my upper limit and lower limit, I'd get 5 cubed, which is 125 over 2, minus 2 cubed, which is 8 over 2. So the exact area under the x squared curve from x is 2 and 5, or my a and my b, I would get exactly 117 over 2 square units. Right? Pretty awesome technique that we are given. Look how much easier that is. And if you wanted to see what this actually found for us, you could go back and do a Riemann sum from the left, right, or middle and see how close you actually got to the exact answer of 117 over 2. Right? That's it. Go practice these. Make sure that you got this down. This is super important for us to continue and move forward, not just in the rest of this chapter 5, as well as that little beginning of chapter 6 that we're going to do, and beyond into Calc 2. Fundamental theorem, pretty spectacular. Keep working hard to understand it and, more importantly, how to do it. Until the next time, Alan, out.